Have you ever wondered what it would be like to ride alongside the beam of light on its journey? This was a question that captivated Einstein more than a century ago. Despite being unable to conduct the experiment himself, he relied on his imagination to devise a thought experiment to determine a realistic outcome. Einstein's intuition led him to believe that the world should feel the same in all frames of reference, moving with constant velocity, known as inertial frames of reference. Whether you are in a train, plane, car, or a room, the laws of physics should apply in the same way as long as you are moving at a constant velocity. This fundamental concept is known as the principle of relativity. To understand this, let's start with the basics. Just how fast is the light? Light travels at an incredibly fast speed of 300,000 km per second when in a vacuum. To put this into perspective, this is fast enough to orbit the entire Earth more than 7 times in just 1 second. While sound travels at a speed of approximately 343 meters per second in air. This means that light can travel much faster than a sound, and that's why we tend to see things before we hear them. For example, if you see lightning in the sky, you will see it almost immediately, but it may take a few seconds for the sound of thunder to reach your ears. This is because the light from the lightning travels much faster than the sound waves from the thunder. Or, as an example, some people appear bright until they start talking. We already know how fast Sonic is from the Sonic movie, which is faster than the speed of sound. But what if we try to travel to Mars at sonic speed of 767 miles per hour? The average distance from Earth to Mars is about 140 million miles, so at this speed, it would take approximately 21 years to reach Mars. However, modern spacecraft can travel much faster, with a speed of about 24,600 miles per hour, allowing us to make the trip in 7 months. For comparison, if we were able to travel at the speed of light, we could reach Mars at its closest possible approach to Earth in just 3.03 minutes. An impressive example of our current space exploration technology is the Voyager 1 space probe, which NASA launched in 1977 to study the solar system. Despite flying through space at an astounding speed of 61,500 km per hour for over 45 years, Voyager 1 is still 22 light hours away from Earth. This means that it takes 22 hours for light to travel between Voyager 1 and Earth. The speed of light is not only universal constant, but also the ultimate speed limit of the universe. Interestingly, for much of human history, it was thought that light didn't have a speed at all, and that it moved instantaneously, reaching its destination at the precise moment it left its point of origin. This belief can be traced back to the ancient Greek philosopher Aristotle, who argued that light traveled instantly and therefore had infinite speed. This idea was supported by other famous scientists of the time, such as Ptolemy and Euclid. However, in 1638, the Italian polymath Galileo Galilei conducted a simple experiment to calculate the speed of light. He placed 2 observers on 2 different hills with a known distance between them. The first observer uncovered their lantern, and as soon as the second observer spotted the light, they uncovered their lantern. By measuring the time intervals between the 2 lamps being uncovered and the known distance, Galileo calculated the speed of light. Although he couldn't detect whether light traveled instantly or not, he concluded that if it didn't, then it must be very fast indeed. The speed of light was first experimentally measured by Hippolyte Fizeau in 1849. He shone a beam of light between the teeth of rapidly spinning gear to a mirror on a hill 8 kilometers away. By increasing the speed of the gear, he reached a point where the reflected light passed through the next gap in the gear and was observed. Fizeau measured the speed of light to be 313,000 km per second, which is within 5% of the presently accepted value. Over the years, many scientists have attempted to calculate a more accurate measurement for the speed of light. In the 20th century, advanced techniques with exotic names such as cavity resonance and laser interferometry allowed for more precise measurements of C. In 1905, Albert Einstein published his theory of special relativity, which is based on 2 postulates. 1. The laws of physics are the same in all inertial reference frames. 2. Speed of light in a vacuum is the same for all observers regardless of their motion. It's important to note that neither of these postulates states that nothing can travel faster than the speed of light. The first postulate asserts that all reference frames are equal with regard to the laws of physics. In other words, there is no difference in physics between the moon and the earth. Despite the difference in gravity between the two, the laws of physics are the same everywhere. The second postulate is that the speed of light in a vacuum is a constant and is independent of the relative motion of the source of that light. This concept caused a paradigm shift in the world of physics as it rejects the Newtonian concepts of absolute time and space. It showed that time is relative to the observer, which was a major shift in the perspective at the time. To illustrate this concept, let's consider a stationary observer who turns on a flashlight at the same instant as someone traveling on a train at a large fraction of the speed of light. This stationary observer would witness the speed of light from their flashlight as being the same speed as the light from the flashlight on the fast-moving train. The only way this can happen is if time within the reference frame of the train is slower relative to the rest frame of our stationary observer. However, the laws of physics remain the same for everyone in every rest frame, so from the perspective of the person on the train, the speed of light is also constant. In their frame of reference, they are stationary and the rest of the world is moving around the train. According to Einstein's special theory of relativity, nothing can travel through space faster than the speed of light. Despite that, people have attempted to achieve such a feat in a variety of ways. One classic method involves shining a laser at the moon, and if you can flick that beam across the moon's surface in less than a hundredth of a second, then that laser spot will appear to move across the surface of the moon faster than the speed of light. If you were standing on the moon, you will see this laser spot move faster than the light coming out of your own laser. However, in reality, nothing here is actually traveling faster than the speed of light. The individual particles of light coming out of the laser are still traveling to the moon at the speed of light. It's only because they are landing side by side in such quick succession that they form a spot which appears to move faster than the speed of light. This phenomenon is an illusion. Furthermore, it's important to note that this faster than the light laser spot cannot be used by astronauts on the moon to communicate with each other faster than light. This is because in order to do so, they would have to send a message to Earth, and then someone on Earth would have to alter their laser. This process would still take place at the speed of light, so no information can be transmitted faster than the speed of light. In summary, while it's not possible for anything to travel faster than the speed of light, there are certain optical illusions that can make it appear as though objects are moving faster than the speed of light. However, these illusions don't violate the laws of physics and cannot be used to transmit information faster than the speed of light. So, what would be like the journey alongside a beam of light? Einstein believed that we will never know the answer to this question because we cannot travel at that speed. At such high velocities, our length would shrink to zero, time would appear to stop relative to an outside observer, and perhaps, the worst of all, our mass would become infinite. When we consider the scale of the universe beyond Earth, light speed no longer appears instantaneous. While Earth is small enough that light speed is almost instantaneous, this changed drastically when we venture further out into the vast expanse of the universe. For example, it takes approximately 1.25 seconds for light to travel between the Earth and the Moon. This may seem relatively quick, but when we consider the vast distance between celestial bodies, this time delay becomes increasingly significant. Let's consider Mars. In the future, when we have colonies on Mars, with thousands or even millions of people living there, the sheer distance between Earth and the Mars will create numerous and fascinating communication challenges. Since Mars and Earth have different orbits around the Sun, Mars varies considerably in its distance from Earth. At its closest, it takes just over 3 minutes for light to travel between the two planets, which is manageable. However, at its farthest point, it will take 22 minutes and 24 seconds, making instant communication impossible. If someone is living on Mars and you send them a message when Mars is farthest from Earth, your message will take over 22 minutes to arrive. Then, Whenever they respond, it will take over 22 more minutes to get back to you. Even if that person responds immediately after receiving your message, it will take around 45 minutes from the time you send the message to get a response, which is the fastest possible response time. Therefore, people on Mars may gradually feel more isolated and separated from Earth, causing human civilization on Mars to become more disconnected from the home planet. As we move further away from Earth, light continues to slow down, creating significant challenges for communication and travel in space. As we previously discussed the Voyager 1 space probe, it has been traveling for 45 years and is now 22 light hours away from Earth. To put this into perspective, the closest exoplanet to our solar system is 4 light years away, while the Milky Way galaxy itself spans a distance of 100,000 light years. The closest galaxy to our own, Andromeda, is a staggering 2.5 million light years away. It seems that we are confined to our cosmic prison for good. However, human curiosity and ingenuity have long sought a way to cheat this limit and exceed the speed of light, or FTL. While we currently have no practical means of achieving FTL travel or communication, there are theoretical threads being pursued by physicists. One such concept is the Alcubierre drive, which proposes the expansion of space behind a spacecraft and contraction of space in front of it to enable faster than light travel. However, the idea faces challenges such as the requirement of exotic matter and enormous energy needs, as well as the risk of destabilizing the bubble through quantum effects. Other theoretical FTL systems such as wormholes and tachyons have also been proposed, but all have one thing in common: they allow for causality breaking time travel. Despite the lack of comprehensive theory of quantum gravity and the diversity of FTL proposals, this fact remains a definitive statement. While the dream of FTL travel and communication may persist, we must also acknowledge the limitation of current knowledge and the need for scientific evidence and objective answers. Thank you for watching.